that I want to talk about today is Kramer's rule. I think there's a problem in your homework set due tonight that deals with what's called Kramer's rule. And so Kramer's rule is a technique to solving systems of equations. So it's a interesting technique. A technique using determinants to solve systems of linear equations. Yeah, it's a pretty interesting, pretty cool technique that works out. And so I'm gonna give you let's start with a very straightforward system. 7x minus 2y equals 3, and 3x plus 1y equals 5. So let's say I want to solve this system, right? There's several ways for us to do it. One way is to transform this into a matrix equation. We get 7, -2, 3, 1 as our coefficient matrix. Then xy is the column vector of the variables that we're trying to solve for. And this matrix, coefficient matrix, is multiplied by its column vector, which gives us another column vector, and that column vector is 3, 5, right? And then we can rewrite this as a multiplied by x vector equals the b vector, and so x is equal to a inverse b. And when we do this, when we apply this multiplication, when we do the multiplication such as this, we get a column vector for the solutions to the system. But the idea behind Kramer's rule, and we can do this, right? We can actually perform this. So what is it? Let's solve this equation. What is A inverse? A inverse, you switch the 1 and 7, and then you negate the 2 and -3, right? And then you divide this by the determinant. And the determinant of this matrix is what? 7 minus -6, so it's 1/13. So something like this, 1/13. And so x will be 1/13. So I'm going to write this as 1/13, -3/13, 7/13, and 2/13. And so this would be 1/13 times 2/13, -3/13, 7/13, multiplies by 3/5. And so we're going to get what? 3 plus 10. We get 1. And then we do 12, 35 minus 35. So this would be -9 plus 35/13. And I get 1 over, what is that, 26/13, which is 2. So I get 1, 2, right? So I get x is equal to 1 and y is equal to 2. So that's the solution. Correct? So we did something that we already know how to do, but what is Kramer's rule? Kramer's rule is more, I guess it's more of a direct, it's like a pinpointing of the solution. So we can, let's say I don't want to know x and y at the same time. I just want to know one of them particularly. So let's say I just want to solve for y first. Solve for y only, suppose. And I don't want to deal with the x value for now. So what we do is we look at the coefficient matrix again, A, which is 7, 3, -2, 1. And since y is associated with the second column of the matrix A, what we do is we replace, to find y, we replace column associated with y with the column vector B. So I'm gonna call this A2. I'm gonna call this A2 because I replaced the second column. So A2 is not gonna be 7, 3, -2, 1 anymore. It's gonna be 7, 3. And then this new column vector is 3, 5. So again, this is the B. This is the B column vector. And so then what is gonna be the Y? Y is gonna be equal to the determinant of A2 divided by the determinant of the original vector of matrix A. So that this is Kramer's rule. So by Kramer's rule, this would be our solution. So let's see what that is. What is the determinant of A2? Well, it's going to be, isn't it 35 minus 9, which is 26? And the determinant of A, we already solved for that, it's 13. So do you see? This equals 2. So Kramer's rule is just applying the determinant twice. And we're doing is we're finding the determinant of a vector, of a matrix, where the column is replaced with one of the column vector B, with the column vector that we have in the matrix equation as a result. So what's the general formula? What's the general idea? The general idea of Kramer's rule. So suppose we have a n by n. No, we have a system with n linear equations and n unknowns. So this looks like what we've seen already, a11 x1 plus a12 x2 dot 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 a1n xn. Let's say this equals b1 and so on and so forth. This is a21 x1 plus a22 x2 dot 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 all the way to a2n xn. This equals b2, and this goes all the way down to bn. This goes away all the way down to ann xn. This is an2 x2. This is an1 x1. Suppose we have this, right? And I want to solve for, so this also gives us what? This gives us the matrix A. So what is A? A is going to be the matrix A11, A12 all the way to A1n. This is A22, A21 all the way to A2n. This is all the way to AN1, AN2. This is ANN. So this is our matrix A, right? And then we have our column vector X, which is X1 all the way to XN. And we have B, which is B1 all the way to Bn, right? This is what we have. This is our system. in its general form. And what we're going to do is we're going to solve for one of them. So by Cramer's rule, to solve for x, let's call it x sub I, and I goes from 1 all the way to n, x sub I is equal to the determinant of a sub I divided by the determinant of a, where a sub I is equal to the matrix A, where the ith column is replaced with B. So this is the ith column. I replaced it with B. And let me just make this a bit more. So I could replace the ith column with B1, B2, all the way to Bn. And everything else is just regular. It's A1, 1, A1, 2, sorry, A2, 1, all the way to AN1. This goes all the way to AN1, AN2, all the way to ANN. So suppose I replace the ith column with the B vector. This is my A sub I new matrix. And this matrix, when I take the determinant of this new matrix divided by the original determinant of the original matrix, that should always get me the value for the ith variable. And that's Cramer's rule. That's all it is. So let's say you have a bigger system, 3x3, 4x4, and you're not interested in finding all of the solutions at once. You're just interested in finding one particular specific value for one of the solutions. Then you apply the determinant of that particular matrix that you're interested in, replacing the ith column divided by the determinant of A. And that's Cramer's rule. So this is another way to solve system of equations. In a sense, it's a more of an iterative fashion. Okay, so any questions about Cramer's rule and the way we perform to get it? Would you like to see another example concretely as to how to use it? Yes, please. Okay, sure. So let's look at a bigger system, okay? So example, say 4x4, right? Let's say negative x, let me call this x1 minus 4x2 plus 2x3 plus x4 equals negative 32. 2x1 minus x2 plus 7x3 plus 9x4 equals 14 negative. So this is a 4x4. x1 plus x2 plus 3x3 plus x4 equals 11. I have x1 minus 2x2 plus x3 minus 4x4 equals negative 4. So suppose I have this system, 4x4. So of course I can rewrite this as what? Negative 1, negative 4, 2, 1, 2, negative 1, 7, 9, negative 1, 1, 3, 1, negative 1, negative 2, 1, negative 4. So this is my coefficient matrix. I got x1, x2, x3, x4 as my column vector. And this equals negative 32, 14, 11, negative 4. So I got A, I got my column vector X, and my column vector B. Okay, AX, B. And suppose I want to find X3. Find just X3.
Professor,
Yes.
where did you get the -1 in the first column, the last one?
Oh, you're right. There is no. Pardon me for
Oh.
that. It should be -1, just +1. That's right.
Thank you.
So according to Kramer's rule, to find just x3 would be what? Determinant of a sub 3 divided by the determinant of a. So I have to find the determinant of a and determinant of a3. But what is a3 though? A3 is the same matrix as A, -1, 2, -1, 1, -4, -1, 1, -2, and then x3 will be what? -32, 14, 11, -4, and then this will be 1, 9, 1, -4. So you see, all I did was I replaced the third column by B. That's all I did. And then I can find the determinant for each matrix here. And what I would suggest, just for time's sake, I'm gonna use a calculator, and you guys can use your own calculator. I think I'll just use the one I have here. So I'll share my screen here. Clear this. So I go to math. I go to second matrix. And then I'm going to plug in the matrix A. This will be 4 by 4. So the 4 by 4 matrix is -1, -4, 2, 1. Then I'll get 2, -1, 7, 9. 1, 1, 3, 1. Got 1, -2. Wait. I think I put 11 where it should have been a 1. So this is 1. This is also 1. -2. 1. -4. Okay, so this is my matrix A. Then what I'm going to do is also include a column vector, 4 by 1. This will be -32, 14, 11, -4. So the first thing I'm going to do is I'm going to just solve this equation the way I would normally do it, which would be to take the coefficient matrix, take the inverse of it, and multiply by the column vector B, right? That's normally the way we would solve the system. And so our solution is 5, 8, 3, -1. So what's expected of us for x3 particularly, x3 equals 3, right? That's what that third number there in the column vector represents. It represents x3. So now I'm going to do the same exact thing. Let me see. Yes, I'm just gonna try to do this really quick. 4 by 4, and I'm gonna do the same exact matrix as A. Instead, the third column will be the values of B. So this will be -1, -4, -32, 1, 2, -1, and then I have 14 instead. I got 9. So -1, 1, 11, 1. I got 1, -2, -4, -4. Okay, and so then now I'm going to find x3 by finding the determinant. So I'm going to make it a fraction. I'm going to say second matrix, go to math. I'm going to take the determinant of A3, which is in my example will be C. So I'm going to take the C matrix. And again, I already know what the answer should be. And I'm going to take second matrix, go to the determinant, and just do A, determinant of A. So close parentheses, when you press enter, you should get 3. You see that? So, and just to make sure, I'm going to specify what the actual values are. So I just want to see what they are. So second matrix of the determinant of C. Let me see what's going on. Second matrix. So I think something's up with my calculator at the moment. But anywho, the answer I get here is 3. Does everybody see how we did that? How I calculated the specific value for x3 by calculating the determinant of the matrix A3, which was the same matrix as A, except that the third column is replaced with B. And I divided it by the determinant of the original coefficient matrix. And when I did so, I got exactly what I was expected to get, which was x3 is 3. And then you can find the rest of them just the same way. x4 would be the determinant of A4 divided by the determinant of A, replacing the fourth column with B of A, and then so on and so forth, x2 and x1. So of course, this takes longer than just multiplying by ax, than doing ax and the A inverse times B. It takes a little longer, but it's more like pinpointing the solution. So you can find exactly, I just want to find x3. I don't want to find the rest of these guys. I just want to find one of them. This is particularly one way of doing so. And it's pretty cool because you're using the same matrix A and just replacing it. It's like there's some kind of like very nice order behind the columns of A, replacing it with B for that particular solution that you're looking for. That's another way, just another way to solve. Okay, so any questions about Cramer's rule? Is that understood? Everything okay? Great, great. So that's the extent of what I want to cover for Cramer's rule. And now let's head back into the world of subspaces, vector spaces, and the like. So what I want to look at is the last thing we spoke about last time was the solution space, right? We talked about vector spaces, and then we spoke about what are subspaces, and we learned how to prove or show whether something's a subspace or not, right? A subspace is a space that contains the zero vector. That's the first thing. The second thing is that it's closed under addition, meaning that if you have a vector, or if you have something in the set that you're looking for, and you have another thing in that same set, so when you add those two set things that are in the set together, they remain in the set. That's called closure under addition. And if that's the second condition, the third condition is if you have a scalar multiplied by something in the set that you're looking at, if you multiply them, then the result will also remain in that set. And that's closure under scalar multiplication. So subspace is a subset of a vector space that contains the zero vector that is closed under addition and is closed under scalar multiplication. So if you can show that a subset of a vector space obeys or keeps those three conditions, then that set is considered to be a subspace of the vector space. And so we showed that for several different kinds of sets. We showed that there were subspaces, and in particular, we finished or ended on whether or not the solution space of a homogeneous system. Okay, so the solution space of a homogeneous system is a subspace. It's a subspace, right? And it's a bit harder to understand this, right, from a more theoretical aspect. But the solution space, so what is the solution space of a homogeneous system? A solution space is the set of all vectors x such that ax equals 0. That's what this is. That's the solution. That's the set. The solution set. The solution set are all vectors that when you multiply a to that vector gives you 0. That's the solution space of a homogeneous system. And what we're saying is that this set in itself is a subspace. And we showed that, right? We show that by showing that, hey, 0 is contained in it. Why? Because a multiplied by 0 does give me 0. So 0 is included in this subspace. We call this W. It's included in W. Right? So the first thing is 0 is in W. And why is that? Because a times 0 equals 0. So that works out. Second thing is, if we suppose we had more than just the 0 vector in W. Let's say we had another non-zero vector. If we have two non-zero vectors, call it V and call it W. What happens when we add V and W? What happens when we multiply V plus W? The question we are really asking is, if we add two things in W, does the result also stay in W? Sometimes it is, sometimes it doesn't. So yeah, so the idea is that is this in W? Is V plus W that we found? So if V and W are in themselves inside W, is V plus W also in W? That's the question. And how do we know whether V plus W is in W? How do we know that V plus W is a part of the solution space? Is if when you multiply it by A, it gives you 0. And what we know about matrix multiplication is distributive. So we got AV plus AW. But both of these, by definition, both of these are equal to 0 because they're in W. Do you guys follow that? So this equals 0 plus 0, which is 0. So yes, V plus W is in W. Yes, so it follows the second condition for a subspace. And then lastly, what happens if I take a vector in W and I multiply it by a scalar C, some scalar number, whether it be 3, 1,000, a million, negative 1.5, whatever. If I multiply that vector that's already in W by some other scalar, is this also still in W? That's the question. By matrix multiplication, I can take out the C out and rearrange the order of multiplication because it's a scalar, not because it's a vector, or a matrix, because it's scalar. So this can be written as A times V. But what is A times V? What is this? This is 0. So of course, the 0 vector times anything will be 0. So yes, this is also true. So if this is true, then C times V is also in W. Because these three conditions are hold, then we say W, or we say that solution space of a homogeneous system is itself a subspace. Why are AV and AW equal to 0 again? Okay, so guys, I know this is a new way, I guess, that you have to become accustomed to in terms of reasoning and arguing. And a lot of this reasoning and arguing is based upon definitions. So what we do is we suppose things are true. We're supposing that V and W are vectors that are inside, that are contained, that belong to this set. They belong to this set. What does it mean to belong to this set? It means that when you multiply your vector, whatever that is, by A, I always get 0. That's what this set is defined as. It's defined as the solution space, or I should say solution set of a homogeneous system. Give me any homogeneous system. We just generalize it now. It's a homogeneous system is a system that looks like this. It looks like a coefficient matrix of some sort. A column vector of some sort equals the column vector 0. This is a homogeneous linear system. So now instead of writing it as a system of equations like this, we write it as a matrix equation. So much simpler. And again, the result of this homogeneous linear system in the matrix equation, a representation of it is equal to 0, the column vector 0. So we're saying that V and W, in this case, V and W are in this set. If V and W are in this set, so if V is in W, what does this imply? It implies that A times V equals 0. That's what it means. If W is in W, then that means that A times W is 0. That's what I mean. That's why they're both 0. Because by definition, I'm saying I'm taking two vectors from this subspace that whose result when you multiply by A gives you 0. And what we're saying is take all those vectors that are in this set. They make up a subspace. They make up a subspace. Why? Because 0 is in it. Why? Because when you take any two vectors inside this set, the sum will still be inside the set. Take any vector, multiply by a scalar, and that result, the vector times the scalar, is still in the set W. And henceforth, W is a subspace of the vector space that you're originally in. This is the solution space of a homogeneous system is a very important space. And so there's different names for it. There's called the solution space, right? But there's also, so notes, there's also other names. So another name for the solution space of a homogeneous system is called the null space. So the null space is the solution set. I'm just going to write just to distinguish it. Is a solution set of the of a homogeneous system of linear equations, which is a subspace. Okay, so we also call this the null space. And there's also one more way we consider or we refer to the null space. We also refer to the null space as the kernel. It's also known as the kernel of a transformation. So it's also called the kernel. The kernel. This is more general. This is more general. When you talk about abstract algebra, they talk about the kernel as well, but it's more of a general term. The kernel of a transformation, where the transformation T goes from Rn to Rm. uh, yeah, it's the solution space of all vectors x such that t of x is 0. Again, we're talking about the same thing. Kernel, null space, solution space. So I hope you guys can think about this a bit more. I hope you start to try to internalize what we're speaking of, the solution space. So normally we've only cared about solving a system, getting the answer, and moving on. Solving the system, getting an answer, moving on. But now what we're going to care about is the actual solution set itself. We're going to care about, hey, if I have a solution set space, let's treat that, or let's consider that now as its own subspace, as its own space. What if we take two vectors in that solution space? What if we add them? What is the result? Or something else that's in the subspace? So then there's a lot more to speak of now when we consider the solution set as a subspace. It's no longer just solutions of a system that we just move on from. We can actually treat that itself as a subspace. Okay. So that's where we left off on last time. And as we continue into this world of vector spaces, we're going to move away from subspaces and head into what's called span. So to talk about span, we have to talk about linear combinations again. We cannot talk about span without talking about linear combinations. So what's a linear combination? So we say if W is a vector in a vector space V, then W is said to be a linear combination of vectors. Let's call this a V1, V2, all the way to Vn, if W can be expressed as the following. Call it C1V1 plus C2V2 plus, these are all vectors, and C's are scalars, where C1, C2, all the way to Cn are scalars. And we call the C1, Cn's, we call them coefficients, right? They're the coefficients. They're called the coefficients of the linear combination. We've talked about linear combinations before, we have, but now we're going to go much more in depth. And this will become our bread and butter. When we talk about vector spaces in its general sense, in its theoretical sense, the idea of linear combinations is extremely, extremely important. So what's a linear combination? Again, a linear combination is basically a sum of vectors with scalar multiples. So we say this is a linear combination. This itself, we'll even forget the W, this itself is a linear combination. We're just defining that sum of scalars the sum of scalar multiples of the vectors, we're calling this some vector, call it W. So we say W is expressed as a linear combination of V1, V2, all the way to Vn. Does that make sense?
Yes.
Does that make sense when we say linear combination? That's what a linear combination is. We're adding scalar multiples of a vector. So any set of vectors that you have, and if you find and if you just add scalar multiples of those vectors together, you get a linear combination of those vectors. Okay. So what is span? What is span? What is span? And I'm going to call this span of S. Span of S is the set, and this is the key phrase, is the set of all linear combinations is the set of all linear combinations of vectors in the set S. And we're going to define S as V1, V2, all the way to Vn. Now, this is a bit more to think about. Suppose S is a set of vectors. So that's what S is, right? S is a set of vectors. Suppose you have a set of vectors. That's what S is. Take all linear combinations. Now, the word all, what does that mean? We know what one linear combination is. A linear combination is, like, for example, 3, put this a 4, put this a 5. And so when we add these up, we get a linear combination. Now here, this is where the theoretical, the generalized perspective has to come into play. Find all of them. But what does it mean to find all linear combinations? How many linear combinations are there? So suppose, example, E1, right? What is E1? And suppose we are in R3. In R3, E1 is what? 1, 0, 0. E2 is what? 0, 1, 0. And E3 is what? 0, 0, 1. Suppose we have these three vectors. What's this? And let S be this the set of these what are called standard basis vectors. And now we're going to know what basis vectors are. What would be the span of S? Or in other words, what would be the span of E1, E2, E3? And so Amir and both Baldwin say, are there an infinite amount? Well, that's the idea, right? What is the span here? It says, hey, take all, this is the set of all linear combinations of E1, C2, right? C2, E2, pardon me, plus C3, E3. Such that C1, C2, C3 are real numbers or scalars. Right. There's an infinite number of scalars, right? Each one of these scalars are on an infinite, are on the number line. And there's an uncountably infinite, we should say, not just infinite. There's uncountably infinite. So this set here is uncountably infinite. which means when you say something that's uncountably infinite, you're saying that you can't precisely count every single one as if you're doing 1, 2, 3, 4, 5. Countably infinite means you can say 1, 2, 3, 4, 5. This is the sixth one. This is the 100th one. This is the millionth one. This is a billionth one. You can do that. But when we have something that's uncountably infinite, you can't count in that fashion. There's just too many. It's just too much. So there's different variation. There's different types of infinities. But yes, the idea is that when you take all linear combinations of C1 of E1, E2, E3, and remember, what is E1, E2, E3? If we look at it from a geometric representation, E1, right? This is 1 here. And then you have E2. This is Y. And you have E3. So when we have a linear combination of these vectors, what do you think the span is? Let's say this. Let's say this. Before we get there, what's the span of E1 and E2? Again, it's the set of what? C1, E1 plus C2, E2, where C1 and C2 are real numbers. It is also infinite, but can you describe to me geometrically what the span of these two vectors only are? What does it represent? And then hopefully you start to see what span actually means. The plane. That is right. Guys, do you remember how we add vectors? These are just sums of vectors, guys. These are sums of vectors. So think about this. Think about adding just E1 and E2. What do you get? Don't you get E1, E2? Don't you get this vector here? Right? E1, E2 would just be this. But think about all the different combinations of the scalars. So we can have E2 being a scalar multiple here, E1 being a small scalar or a negative scalar. And so when you start to see all possibilities of the sums of different scalar multiples of E1 and E2, the result becomes what? The plane, the XY plane. The span of E1, E2 is the XY plane. I don't know if you guys see that. The XY plane in its entirety consists of all linear combinations of E1 and E2. Think about that. If that doesn't make sense, if it doesn't register, then think about it. Second thing, what is the span of E2, E3, for example? Again, it's the linear combinations of E2 and E3. All linear combinations of that would give you what? The YZ plane. That's right. That's right. And so, Baldwin, you're onto something. What happens if you take the span of E1 and E3? Well, E1, E3, you're only going to be in this two-dimensional plane, right? So we have the XZ plane. Do you guys see what's happening here with span? Do you guys see what span is starting to be? It's more than just saying it's a linear combination. Now we can see that it's a geometric visualization of it, right? That's what a span is. We take every vector in this set and we find all possibilities of adding different scalar multiples of those vectors. Geometrically, in this case, it's a plane every single time. And so then now the question is, going back to our original question, what's the span of these three vectors? E1, E2, and E3. And so Baldwin, what do you say, Baldwin? It's the what? It's the XYZ space. the span of all three vectors at the same time gives me every possible vector in this space, every single one. So it covers the entire three-dimensional space. So you can say the span is equals R3. So every linear combination that ever can exist between E1, E2, E3, when you take all of them together, that makes up the entire three-dimensional space. And that's what span is. Baldwin, yes.
Just to see if I get this, so like the span would be basically every possible outcome we have.
Say it again. Span of what?
So the span would basically be every possible outcome we have in
Every
the
possible
space.
outcome of the linear combination of the vectors.
Gotcha.
So it's always about the linear combination. And if you just look at it from an analytical perspective, just by this, if you just look at it as a sum, you kind of don't get the full picture. When you look at it from a geometric perspective now, right? You're taking vectors and you're adding vectors. When you add vectors, you get new vectors. And then when you make every single possible sum of those vectors, you start to see that you're covering a whole plane for these ones, right? You're covering a plane because every point on that plane can be represented somehow as a linear combination of these two vectors. So when you have two vectors such as this, it can span a plane. When you have the three vectors, it spans a three-dimensional space, and so on and so forth. So for example, I'll give you another example. What would be the span of E1? If I just gave you one vector, what would be the span of E1?
It would be X.
It would be
X plane.
The x-axis. So the span of a single vector, if you think about it, you're taking all linear combinations of just one vector, which means you're taking all scalar multiples of just one vector. If you find all scalar multiples of one vector, you're basically saying, take this one vector and find all scalar multiples. That would span just one single dimensional line, which would be the x-axis, and so forth. Span of E2 would be the y-axis. Span of E3 would be the z-axis. And again, we're only dealing with vectors in R3. Then you can have things in R4, R5, and other spans, being spans of matrices, spans of polynomials. So that's how span gets generalized to other vector spaces. This is a very particular kind of span where we can geometrically understand what's going on. So again, this idea of linear combinations can be applied to any vector space, but the geometric understanding is really boils down to this kind of geometrically understood space, which is R3, R2, and the like. But we can always go back to something that we are accustomed to and then generalize it, abstract it to other vector spaces. Does that make sense? Yes. So now I want to talk about is the span of S a subspace? Is it a subspace? So the first thing is zero. Is zero in the span of S? A subspace of a given vector space V. I know it's very generalized, isn't it? Like this idea. So suppose we have a vector space V, and we have a subset of vectors, which is S. So let me make this a bit more clear. So is S where S is a subset of vectors in V, which would be what? So S can be just a set of vectors, V1 all the way to Vn. It's not a specific size, it's just a subset. So it's a certain number of vectors in V. If I take a certain subset of vectors in a vector space V and call that subset S, if I take the span that's in, if I take the span of everything in the subset S, does this constitute as a subspace of V? How do you determine whether a subset of a vector space is a subspace of that vector space? We have to consider those three different conditions, correct? So is 0 a subspace of S? What does this mean? What would this have to mean? It would mean that if you take vectors C1, V1 plus C2, V2, is there a linear combination that would give me the 0 vector? Yes. Make all the CIs, right? C1, C2, all the way to Cn. Yes. Make them equal to 0. So Ci equals 0 for all I goes from 1 through n. Take every coefficient, make them 0. Multiply 0 by the vector 1 plus 0 times vector 2 all the way to 0 times vector n, Vn. If you take this sum and make them all zeros, this will give me 0. So yes, 0 is in it. 2, if, let's call this another, if W is in S and U is in S, is W plus U also in S? So again, what does it mean to be in S? It means that you're a linear combination, correct? Of V1 through Vn. So this means, so what does this mean? If W is in S, this means that W can be written as a linear combination of V1 through Vn. So what that linear combination looks like, I can say it's A1, for example. I can just make up letters. A1 V1 plus A2 V2 plus all the way to AN Vn. That's what this means. I'm in the set S, in the span of S. Sorry, I should say span, pardon me, not S. W is in the span of S. And U is in the span of S. Is U plus W in the span of S as well? Again, what does it mean to be in the span? It means that you're a linear combination of V1 through Vn. So W, I say it is in the span. If it's in the span, I can write it as a linear combination. If U is in the span, I can also write it as another linear combination. I'm gonna call it B1, V1 plus B2, V2 plus all the way to Bn, Vn. Does everybody follow that? If I add these together, if I were to add W plus U, would this new vector also be in the span of S? Equivalently, if I add W plus U, is this new vector a linear combination of V1 through Vn? That's the equivalent question. When you add these two things together, what's going to be the result? Don't I get A1 plus B1 V times V1 plus A2 plus B2 times V2 all the way to AN plus BN times Vn? Isn't that the result? And what am I saying with this? Exactly. All of these, A1, B1, A2, B2, AN, BN, I can call them some other coefficient. Call it C1. So let Ci equal AI plus Bi. Then this becomes C1 V1 plus C2 V2. Plus, I just renamed them. Cn Vn. What does this mean? This means that W plus U is in the span of S. So I'm showing this from an algebraic point of view. So if I take something in the span of S, I take another thing in the same span of S, which is just another linear combination of the same vectors. When I add those two vectors together, I'm still in the span. I still can represent that sum as a linear combination of those original vectors, V1 through Vn. And so, yes, this is true. And then lastly, if V, you can call this anything you want, V is in the span of S, and call it K. K is a scalar. I should just say K is a scalar. Is K times V also in the span? Is this also in the span? So if V is in the span, what does that mean? I can rewrite this as a linear combination of V1 through Vn. Use letters. You call this D1 V1 plus D2 V2 plus all the way down to Dn Vn. What happens when I take K times V? What does this become? Doesn't this become K times D1 V1 plus D2 V2 all the way down to Dn Vn? But when you multiply, don't you distribute the K? Don't you get K D1 V1 plus K D2 V2 plus all the way to K Dn Vn? And then can't you reassociate this? And so what do I still have? What do I still have? I can still represent KV as a linear combination again. This is a linear combination of what? Of V1 all the way to Vn. So what did I just show? KV is still in the span of S. Because these three conditions hold, then what do we say? We say we can conclude that the span of S is a subspace of a vector space V where S is a subset of vectors in V. So take any vector space, I don't care what it is, take a subset of those vectors, take a section of it. If you take the span of those vectors, that creates a subspace. That is always a subspace. Does that make sense? Any questions? Any questions about this? No question.
Professor, I have a question. It's kind of a little bit off topic, but what is like the importance of kind of concluding this?
What is the importance? The importance of concluding that span of a vector of a subset of a vector space is a subspace?
Yeah.
Well, the thing is, we care a lot about subspaces. And there's different types of subspaces. So we're talking about the solution space of a homogeneous system. That's a subspace. So all we're doing right now is identifying everything that are subspaces. So the idea, the question really should be, what's the importance of subspaces? because all we've been doing so far is proving whether or not something is a subspace or not.
Yeah.
Yeah. So subspaces are just another way to divvy up a vector space. So a vector space is this whole thing, right? It's a set of vectors that have very nice algebraic properties where you add them, you get the same thing. It's still in the vector space. When you multiply by a scalar, it's still in it. And there's all these other 10 axioms that or those 10 properties that we showed in the first lecture on vector spaces that make up a vector space, right? A vector space is a set of vectors that have two operations, one addition and one scalar multiplication. And so we've seen various examples of vector spaces. They can be literal Rn, right? R3, R4, R5, all those are vector spaces. They can also be the set of matrices. Those are vector spaces. We also saw that there's an idea of functions, all the functions, also a vector space, and so on and so forth. But then now we want to see, hey, now we have a vector space. What other ways can we interpret or organize our vector space as? Is there more underlying structure behind this vector space beyond just having those 10 properties hold? And then we're having more specific kinds of a subspace is just simply just a vector space within a vector space. That's why it's called a subspace. It's a subset of a vector space that happens to be also another vector space. And that, the importance of it, that's like a very, I guess, broad statement. But hopefully slowly you'll see the importance of it. Okay, so right now we're just building up. Yeah, we're just building up the toolbox, right? So what you do know is that when we talk about vector spaces, we really care about subspaces. We really care to know whether within the vector space itself there exists another vector space. And so we start to see that there's a vector spaces that have subspaces to them. And now there's different kinds of subspaces. And this is a pretty nice one, a linear combination of sets of vectors. When you take a linear combination of those things, and you take all the linear combinations, you form another little subspace. And it gets more complex as you build up this idea of subspace. It comes to a point where you can break down vector spaces into a union of subspaces, but that gets a little bit more in depth. But for now, what I want to do now is I want to see whether we can determine if a vector that we have is in the span of another vector, of a set of vectors. So let's see. Okay, so I'll give you some examples here. Suppose we have different vectors. So now these vectors are matrices. A is 1, 0, -1, 2. B is 0, 0, 1, 1. C is 0, 0, 1, 0. And D is 2, 1, 0, -1. And I have another vector. Let's call this W. Let W be the matrix 1, 2, 2, 4. The question is W in the span of A, B, C, D? That's going to be now the typical question. And you see here, I'm using vectors, quote unquote, right? Because these are matrices, but they're part of a vector space. And that vector space here, what's that vector space? What's the underlying vector space? The underlying vector space is is the set of 2 by 2 matrices. Remember we talked about the set of n by n matrices being a vector space. So we have a subset of those of that vector space. We have these 4 vectors, or in this case, we have 4 matrices. And using these 4 matrices alone, if I have a linear combination of these matrices, is there a linear combination of A, B, C, and D that gives me the vector W? Do you guys understand what I'm asking? So if W, is there a scalar A for A, B for B, C for C, and D for D? Is there a vector space? Is there a linear combination of A, B, C, D that gives me W? In other words, so this is the more nitty gritty, this is a more concrete example. If I have something like this, A, this becomes 1, 0, negative 1, 2, plus B, 0, 1, 0, 1, plus C, 0, 0, 1, 0, plus D, 2, 1, 0, negative 1. Do you guys see what's happening? I'm trying to see whether there exists A, B, C, and D, so that when I put them in here, I have a linear combination that results in this. Do you guys see where to go from here? The inverse? Well, not quite as of yet. We don't have the inverse of what exactly are you speaking of? So do you see how we have to incorporate the idea of scalar multiplication for matrices? What would be the scalar multiplication here? Wouldn't I get A, negative A, 0, 2A? Wouldn't this be 0, 0, B, B? And then I get 0, C, 0, 0? And wouldn't I get 2D, D, negative D, 0? This becomes 1, 2, 2, 4. And do you see how now the world of matrices can kind of be represented as a vector? Because how do you add matrices again? We add by entry, by components, right? So wouldn't this be the same thing as saying A plus 2D? This is negative A, B plus C. This entry here would be D, and this last entry would be 2A plus B minus D. Do you guys see what I just did here? I added these 2 by 2 matrices all at once, and I got another 2 by 2 matrix, and look what I got. 1, 2, 2, 4. And then don't I know that each of these components has to be the following? 1 has to equal A plus 2D. And then 2 has to equal negative A plus B plus C. And then 2 has to equal D. And then 4 has to equal 2A plus B minus D. And this is a simple example. 2 is already equal to D, so you can plug this in and so forth. But what I want to do is I want to bring this full circle, and look, I can create a matrix equation in itself. I can create a matrix where the column here is all the A's, the coefficients of A, all the coefficients of B, all the coefficients of C, and all the coefficients of D. So this would be what? 1, negative 1, 1, negative 1, 0, 2. B values will be what? 0, 1, 0, 1. C will be what? 0, 1, 0, 0. And D will be what? 2, 0, 1, negative 1. And this here would be A, B, C, D. And this will equal 1, 2, 2, 4. Do you guys see what I'm doing? And so, Mir, the question would be, does this have an inverse? That's the question. Does this coefficient matrix have an inverse? Yeah, Tassif, this is way more interesting than adjoints. Like I said, we're getting into like the meat and potatoes of linear algebra. This is like we're getting into the core of it. So we're going beyond just the idea of system of equations, And now we're dealing with subspaces, we're dealing with span. And look at this question. Always go back to the original question. What's the original question? I have these four matrices that come from a vector space, which deals with the sets. It's a set of all 2x2 matrices. So take all the vector space and all of the 2x2 matrices, all of them, and take only four of them. And I selected these four. And now I have this other matrix, call it W. And I'm asking myself, is W in the span of these four matrices? In other words, can I write A, B, C, and D as a linear combination of those four matrices that results in getting W? And so when I write this out, I end up writing a system of equations. So the idea of span for this problem results in solving a system of equations, which I can revert this into a matrix equation in itself. So I can think of this as a system in R4, but I'm really talking about M22. So you see how there's a connection between the set of 2x2 matrices and the fourth dimensional space. So there's this idea called isomorphism, which is how certain spaces are kind of structurally the same, though they may be kind of distinct in their representation. Of course, that gets more abstract, but that's the idea. And now the question of whether or not this vector, this matrix W is in the span of A, B, C, and D, that question boils down to solving a system of equations using a matrix equation and asking the question, is this matrix invertible? That's what it boils down to. If this matrix is invertible, what's true? If this matrix is invertible, then a solution exists to this equation. We know what A would be, what B would be, what C would be, what D would be, what D would be, what D would be, what D would be. So if I know all of these values, what am I really saying? It is a tongue twister. What am I really saying? I'm saying that there exists A, B, C, and D. There exist scalars for a linear combination of A, B, C, and D, which results in W. That's it. That is the result. So the result is the determinant equal to 0 or not equal to 0? You see how it boils? This is so cool about, that's what's so cool about linear algebra, is that you have this abstract notion of things and then you boil it down to some computational aspect. So that's how, like, it's so broad. It's such a it covers a large spectrum of both theoretical aspects and computational aspects at once. That's what's so beautiful about linear algebra. So it brings it back together. So the question is this invertible? Is this matrix invertible? Or is the determinant of this matrix equal to 0 or not equal to 0? That's the question. So if I compute the determinant, let me compute the determinant of this matrix 1, 0, 0. And the reason why I can do this by hand is because there's a lot of zeros. So which row or column would I perform cofactor expansion upon? It would be row 3, wouldn't it? Because I have all these zeros. So I know all these zeros here will be taken care of, and I only have to worry about this 1. So then this is what? This is in the 3, 4. So what is this going to be? Cofactor expansion. I get what? I get 1 times C34. Remember what C34 is? It's equal to -1, 3 plus 4 times the minor of 3, 4. And what happens with 3, 4 here? The minor is going to be what? And this will be negative. So this will be negative, the absolute value of the determinant of 1, 0, 0, -1, 1, 1, 2, 1, 0. Does everybody follow me? And again, I only care about whether or not this determinant is 0 or not. So then here, I can also do a cofactor expansion along the first row. So along the first row, what happens? These cancel here, these cancel here. So this becomes, there's still negative out there. This becomes the determinant of 1, 1, 1, 0. And now, can you see here what the determinant is? The determinant is 1. What does this mean? It means that the determinant is not 0. What does it mean for a determinant not to be 0? It means that my matrix is invertible. What does it mean that my matrix is invertible? That means that the solution exists. What does it mean that the solution exists? There's a unique solution that exists. What does it mean? It means that there exist values A, B, and C, and D that make this equation true. If this equation is true, using certain values of A, B, C, and D, what does it result in the original problem? There exist scalars A, B, C, and D that can form a linear combination of the matrices A, B, C, and D that results in W. So overall, what's the answer? What's the overall answer? Is that yes, W is in the span of A, B, C, and D. Does everybody follow what I just said? I hope so, because it's a lot. It's a lot to break down like that. But yeah, I'm glad it makes sense. I'm glad it makes sense. Good, good. So again, lengthy but logical. Yes, it is lengthy, isn't it? But hopefully now when you start to get more experience with this, it becomes a little bit simpler. And what I'm trying to show you is that these are elements of a vector space. Okay, so you can have things that are not necessarily vectors in the classic sense, where you have a column vector or a comma delimited form of a vector. These are also, in a sense, quote unquote, vectors, because they're from a larger vector space, which is the vector space M22. So it's the word vector is kind of used in a broader sense. Okay, and then you can also deal with the same kind of question with polynomials. Polynomials are themselves elements of a vector space. And it's the same kind of idea. Same kind of idea. So how do we determine whether something is in the span? We always have to form this kind of system and see whether the determinant is of that matrix is whether it's the determinant of that matrix is 0 or non-zero, which would indicate whether the matrix is invertible or not, which would indicate whether a solution exists or not for those scalars. So that's really what it boils down to. If these scalars these scalars become my unknown, they're the unknowns in this system. If there's an inverse to this matrix, then there's a solution. If there is no inverse to this matrix, then there is no solution, which would indicate, so let's say this determinant was 0, which would indicate that this matrix is not invertible, which would indicate that the solution to the system does not exist, which would indicate that this let's suppose this matrix is not in the span of this set of matrices. That's what that other possibility would be. So either you're in the span, which means that there does exist a scalars, which would mean that the determinant of this matrix would be non-zero, which would mean that this matrix is invertible. You see how all these things are connected? All those statements are equivalent statements. That's why it's important to understand the equivalent statements. How the determinant of a matrix implies the invertibility of the matrix, which implies the existence of solution of a unique solution, which implies whether or not something's in the span. Like all of these things are connected. So it's good to make those connections. Okay, let me see if I can do one more of these, and then we'll move on to linear independence. Okay, I'm gonna do a polynomial example, and then hopefully you can fill in the gaps yourselves. So suppose I have polynomials in P, what is this, P2. So in P2, remember in P2, this is the set of all polynomials that are of degree less than or equal to 2. So in P2, we have, I'm gonna call this little p, okay? Little p is 2 plus x plus 4x squared. Okay, I'm gonna treat this as P2. Okay, so that P1 and P1, P2, P3 are in P2, in the polynomial space P2. Did we touch on solving for the area of a quadrangle? Quadrilateral? Oh, that one I think you have to apply the idea of finding the area of a triangle. Like there's a quadrilateral, right? You can split that up into triangles. And we know how to find the area of a triangle using vectors. We talked about that. Yeah. So P1 is this, P2 is 1 minus x plus 3x squared, and P3 is 3 plus 2x plus 5x squared. And the question is this new vector P, is P negative 9 minus 7x minus 15x squared in the span of P1, P2, and P3? Is it in the span? If so, express P as a linear combination of P1, P2, and P3. Do you guys see the question? The two-part question? I have a polynomial space of degree 2. I have 3 instances of those elements, P1, P2, P3, right? These are all quadratic expressions. And I have this new quadratic expression, and I'm asking myself, is this new quadratic expression in this polynomial of degree 2, is this in the span of P1, P2, P3? Is it in the span? In other words, is there a linear combination of P1, P2, P3 that results in P? Is there? If so, express it as a linear combination. It's very similar. You see, Sam, it's the same thing, but it's different, but it's the same. It's one of those things. It's the same, but different, but the same. Why is it different? Because we're dealing with different elements. We're dealing with polynomials. We're not dealing with matrices, but inherently it's kind of the same kind of problem because we're dealing with span. Right, component by component. And how are the components, quote unquote, here divided up? The components are based upon the coefficients of the terms. So you see how this here can be considered in a sense as 2, 1, 4, where the first coordinate is the coefficient of the constant, the second coordinate is the coefficient of the linear term, and the third coordinate is the coefficient of the x squared term. So all of these can be considered as vectors in a way. Do you see that? So then the question is this, look, the question is P equal to C1 P1 plus C2 P2 plus C3 P3? Do you guys see that? It breaks down to the same thing. So this becomes what? The long way would be what? C1. C1 is what? 2 plus x plus 4x squared. C2 times 1 minus x plus 3x squared plus C3, 3 plus 2x plus 5x squared. When you do the algebra, when you do all this algebra, what do you get? You get 2C1 plus C1x plus 4C1x squared plus C2 minus C2x plus 3C2x squared plus 3C3 plus 2C3x plus, pardon me, there's not enough space here, 5C3x squared. And then what am I going to do? What am I going to do? I'm going to associate everything of the same kind. What do I mean by the same kind? All the constants, put them together. So 2C1 plus C2 plus 3C3. That's one thing clumped together. The next thing are all the linear terms, plus C1 minus C2 plus 2C3 times x. And then I'm going to add all of the constants, all the terms that are x squared. So I got 4C1 plus 3C2 plus 5C3. You guys see what's happening? And this equals P. But what's P? P was this equals -9 minus 7x and then minus 15x squared. This is P. This is the sum of P1, P2, P3. This is the result, P. Now, in order for these two polynomials to be the same, the components have to be the same, right? So look what I get. The result is what? 2C1 plus C2 plus 3C3 equals -9. C1 minus C2 plus 2C3 equals -7. 4C1 plus 3C2 plus 5C3, this equals -15. Do you see what we just did? We went from having a polynomials equal to polynomials to having a system of equations again. And then what is this system of equations? Can be represented as a linear combination, system of a matrix equation. So this becomes 4, 3, 5. The column vector becomes C1, C2, C3. And the column vector here is -9, -7, -15. So the question again of whether a polynomial is in the span of three other polynomials boils down to this matrix equation and asking whether the matrix is invertible or not. If the matrix is invertible, the determinant is 0. If the determinant is 0, that means that this would be a singular matrix, which would have no solution, which would mean that it would not be in the span because there's no solution for the scalars. But if this determinant is non-zero, it would mean that it's non-singular, which would mean that the matrix is invertible, which would mean that there's a solution that exists for C1, C2, C3, which would mean that the polynomial is indeed in the span of the three polynomials that we started with. Does this make sense? So the idea again boils down to whether this determinant is 0 or not. That's what it boils down to, guys. So the idea is the determinant equal to 0? So we can compute this, can't we? Really quick. How do we compute a 3x3 matrix determinant? You guys remember? We can do the little trick where we include the two columns here, 2, 1, 4, and 1, -1, 3. And then we can compute the diagonals here. And then compute the products of the diagonals here. So 3 times 1 times 3 is 9. This becomes 8. And this becomes -10. And we add these up together. And then these here, we're gonna, so this will be what? This would be 7. Sorry, I should make this 7. And then when you multiply these here, you get -12. 4 times 3 is 12. This is 5. So when you add these together, what do you get? You get 5. And then you take these two numbers and what do you do with them? You subtract them, don't you? And what's the determinant? Determinant is what? 2, which is what? Not 0. What does that mean? Invertible. What does that mean? Unique solution exists. What does that mean? That means that P is indeed in the span. So conclusion, P is in the span of P1, P2, P3. And I'll leave as an exercise for you guys to find what those coefficients are. And again, you can use Kramer's rule to find those individually, or you can just apply A inverse times this vector here, and you get C1, C2, C3, and those scalars are the scalars needed to multiply each of these polynomials so that it gives you the linear combination. So does everybody follow me? Is everybody clear with this? Does everybody understand span now? Is this understood? So it sounds like you'll be wanting us to calculate determinants by hand. No. I actually, eventually, I'm not gonna make you do that. For these kind of things, I think what's more important is determining whether or not something has a non-zero determinant and what that implication is as far as the span of a set, whether something's in the span of a set. That becomes more important than whether if you actually know how to compute the determinant. The reason why I'm computing it by hand is because currently my graphing calculator is going crazy right now, so I can't actually use it and to show you guys what my calculations are. So I'm doing this by hand for that reason. But regardless, you should know how to do it by hand as well. So yes, of course. But on the test, I'm not going to be testing you so much on whether or not you can compute the determinant. I'm going to be testing you more on if you do compute the determinant, what does that number tell you and how does that relate to the question? That becomes more important now on the second time, for the second exam. Okay, so you can compute the determinant with your calculator. I have no problems with that. I'm more interested in, do you know what it means? What the significance of the number that you get? Do you know what the implications are? Okay, now that we understand span and linear combinations, so this idea of linear combination, we'll not leave that yet. We'll touch upon span again, but now we're going to talk about what's called linear independence. And then eventually on Wednesday, we plan on connecting these two things together. If you have a set of vectors that span and a set of vectors that are linear independent as well, we'll talk about what are called bases, a basis vector. And then that's going to go back to the standard basis vectors that we started with, E1, E2, E3. But again, what is linear independence? So a linear independence, a set of vectors, call it S, V1, V2, all the way to Vn. A set of vectors S is said to be linearly independent if for if and only if, I should say, if and only if the only coefficients, aka scalars, if the only scalars that satisfy the equation, and what equation are we talking about? C1 V1 plus C2 V2 plus all the way to Cn Vn. If this equation, which we'll see how this is a homogeneous system, if this equation has the only scalars solutions being C1 equals 0, C2 equals 0, and Cn equals 0. That's what it means to be linearly independent. Okay? So no zero vector. What do you mean by that, Mir? What do you mean by no zero vector?
Like that any v sub I can't be the zero vector.
Right. So we'll talk about that. So note, any vector set of vectors that include a zero vector is always linearly dependent. So a lot of this happens, guys, at this level now. You have to be able to find, given what they tell you, you have to find like the converse or the opposite. So if I tell you that a set of vectors is linearly independent, if a linear combination of those vectors equaling to 0 only results in having the solutions or the scalars being zeros, they have to all be zeros. If all of these are zeros and only zeros, then these vectors that we have here are called linearly independent. So what does it mean to be linearly not independent or linearly dependent? That means that one of these scalars are not zero. Now, what does that mean with zero vectors? So if one of the vectors here is a zero vector, do you notice that this scalar could be anything other than zero? It doesn't have to be zero. So the moment I have a vector in a set of vectors that is a zero vector, in this linear equation, in this equation that I have here, the scalar that's associated with that zero vector could be anything because it always results in zero. What does that imply? That implies that the set of vectors that include the zero vector can never be linearly independent. They're always linearly dependent by definition. So again, this is a little strange, right? At first, you're like, what does this actually mean? Well, we can start with the basic ones. E1, E2, and E3 are linearly independent. How is that? Why is that? Why? Well, what is C1, E1 plus C2, E2 plus C3, E3? When you make this equal to 0, what does this equal to? What does C1, C2, C3 have to be? Well, what is E1 again? 1, 0, 0. What is C2, E2 again? 0, 1, 0. What is C3, E3 again? 0, 0, 1. And this is 0, 0, 0. But then what do I get, guys? What do I get? I get C1, 0, 0 plus 0, C2, 0 plus 0, 0, C3 equals 0, 0, 0. But what is this going to be equal to? C1, C2, C3 equals 0, 0, 0, which equals what? C1 equals 0, C2 equals 0, C3 equals 0. That's the only possibility. So that henceforth, E1, E2, E3 are linearly independent because the only scalars that work in this system is equal to 0. I could have also looked at it from a different perspective. I could have also made this into a system of equations. I could have created, what's the system of equations that I could have created? I could have created a system of equations from right here. I could write this as 1, 0, 0, 0, 1, 0, 0, 0, 1, C1, C2, C3 equals 0, 0, 0. Do you see how this is a system, a homogeneous system? So this homogeneous system has a unique solution if the determinant, again, is non-zero, which clearly it is because it's the identity, and the determinant of identity is 1, which is not 0. So you see, do you see how this sort of follows from spanning? You see how this is sort of like a linear, no, not the sort of, this is a linear combination. But do you see how this is a very specific vector that we're dealing with? Basically, the question is, so since 0 is in the span of every vector, is in the span of every subset of vectors, right? You can always write 0 as a linear combination of vectors. The question is this linear combination of vectors that give me 0 is the only way to represent a linear combination of vectors of V to represent 0 is the only way having the scalars being zeros. If that's the case, then those vectors are considered to be linear independent. If it's not the case, if there's more than one way of representing these C's other than having zeros all across them, then we would say that they're linearly dependent. Does that make sense? No. So whenever they ask you, are these set of vectors linearly independent, you basically have to set up this equation again and again. Set up this equation, create the matrix equation, and determine whether or not that matrix is invertible or not using the determinant. So this follows a bit from spanning, but now it's very specific vector. It's the 0 vector. And the scalars have to all be 0. Okay. So I think we'll finish up on Wednesday. So for those of you who have questions about this homework assignment, you can meet me in office hours using the link that I sent you last week, and we'll take it from there, guys. So, and the recording here.